Good afternoon to you all. My name is Donna. I come from Israel. My CFD department is a joint venture of OffStream Studios and Netanel engineers. Our department is comprised of engineers from fire safety from Netanel engineer, and our leading engineer is Netanel. I'll be speaking today about underground parking garages, changing perception on smoke control criteria, and combining an integrated smoke system and ventilation system for that matter. And we go the other way around. Okay. Underground parking garages spaces are usually a little bit more difficult to handle since they are all comprised of large spaces. They come from different sizes and different shapes, and some of them are partially opened or partially closed, or completely closed or opened. And they are made for different uses, and they're comprised of different congestion amounts and capacity. One of the things that underground parking garages has in common is low-rise ceiling, is low-height ceiling. When we're talking about smoke layer, we usually are trying to get a smoke layer under 1.8 and 2.5 meter, and most of the underground parking spaces are usually not higher than 2.5 or 3 meter height. So they vary between different buildings and the underground smoke. When designer comes to deal with underground garages, they're facing three main challenges. The first challenge is to maintain tenable air quality, since underground parking lots are usually underventilated. You have to deal with that problem. The second problem underground parking garages have is during emergency times for smoke control and management in order to keep egress routes and rescue team routes clear of smoke. Well, the third challenge that we have is integrated both ventilation and smoke control issues into one system without over-designing it. On the air quality issues, well, the challenges on air quality is keeping fresh air, is getting rid of smoke haze, of nitrogen oxide, carbon dioxide, and the most pressing issue is keeping tenable carbon monoxide levels. So when we look at the codes and the regulation that are addressing air quality in underground spaces, we see that there is a big variation between national, international, and local codes. You cannot see like one guiding lines to what to do or how much air to extract and introduce to the premises. You can see at NFPA 88, not A, that is a mistake. You can see under NFPA 88 that specifically addresses underground spaces that they state 5 liters per second per meter square of gross floor area. NFPA 502 states CO, ppm, threshold, exposure time, but just for times of emergency and not for time for normal ventilation operation. The ANSI ASHRAE standard, for example, states a fixed ventilation of 7.62 liters per meter square and an exposure threshold for 8 hours for a low ppm exposure and 1 hour for a higher ppm exposure of 35. When you're looking on the other issue of smoke control management, when looking at the challenges at hand, we are trying to minimize the impact of smoke upon the occupants inside the area. Although underground garages do not usually hold a large number of occupants, they still do. And when these people are at the premises, we need to keep them safe and away from the smoke. The second thing is maintaining the tenability condition when those people present need to egress and when the people from the people from the rescue team comes inside to deal with the fire. So when we look at regulation regarding the second challenge, and smoke control, we can actually see that there are non-existent in most of the codes that we are using. In Israel, we adopt the NFPA standards, and when you're looking for something to tell you exactly what to do and how much and how to design the system, you don't find any codes that are dealing with that. I saw some codes and some issues dealt with in Japan when looking into and digging into the regulation. So usually when you go and you design underground parking garage, you utilize default codes. You use NFPA 88, you use NFPA 92B, which is storage occupancy of vast spaces, which is quite similar in the magnitude of space to underground parking, and use NFPA 204 for standard for smoke and heat ventilation, which actually has the problem with the tenability condition of the smoke layer height. Code 204 states that 1.8 to 2.5 smoke layer height maintained during evacuation. Now in Israel, authorities actually require a specific 6 air changes. Doesn't matter what, doesn't matter why, it's 6 air changes. And they expect the smoke to completely be cleared from the premises. They do not believe in smoke control. They think it's the same. So most of the time, it's really hard to establish those goals. I went the other way around, excuse me. Yeah, so with this integrated needs and integrated requirements, most of the designers find themselves at the end of the day designing systems that are based on vents, which is normal, which are based on jet fans for congestion points, and which are usually a little bit more complex than what the system could be. Now, a complex system has a big problem with cost effectivity. When you have a big system with a lot of ducts, vents, shafts, it takes a lot of money to maintain it and a lot of power to operate it. So it's consuming on energy and it's consuming on maintenance. And the last thing, which is more important to, let's say, a more uptown building, I will call it, is it's not aesthetic. Usually when you go into underground garages, you see all those ducts running around your head. And it's, well, far from being pretty. So our goal as designers, sometimes and most of the times, is meeting the fire and rescue authority requirements, meeting health and environmental authority requirements for air ventilation and regular use, designing a viable, cost-effective, energy-saving, low-maintenance system, which is also aesthetic to the eye, and designing a system that is neither over-designed nor under-designed to meet the requirement safety and egress measurements. So what we present and what I present in this article today is an alternative perception and smoke control criteria. Instead of looking at smoke control criteria for tenability issues in underground parking garages is the smoke layer height, because that is inapplicable, we are going to suggest a new way of looking at it. The alternative proposal that we propose is based on performance-based design, and it's meant to achieve reasonable life safety level, such as protecting occupants not intimate with the initial fire development and during the time to be evacuated, relocated, or defend themselves in place. And the other thing we do is maintaining tenable condition on egress routes, providing clear access for the rescue team to get inside, deal with the fire, do their job, and keep us all safe. The alternative perception is based on smoke zone. Instead of looking at an underground space as one fire zone or one large area, we divide it into separate smoke zones. The smoke zone is predefined areas in which smoke layer are fire effect will be restricted and maintained as far as steady state reaches, preventing smoke from traveling between stories inside the structures, since in underground parking garages you tend to see when fire builds up and smoke layer builds up, it travels through the ramps to the other levels. And that's one of the problems we're trying to hold. Maintaining clear egress routes and incorporating a push and pull method, which means, which most of you probably know, is exhausting from one side and pulling from the other side as far as you can get them to make barriers for the smoke not to enter the egress routes. And the last thing we use is smoke screen in order to fragmentize the vast area of the underground parking lot. Okay, now, I went the other way around again. That doesn't, okay, excuse me. Regarding the air quality control ventilation for daily use in underground parking garages, the reason we need to look at a different way of providing proof of sufficient ventilation in underground spaces is the fact that you can't just not go and say most of the regulations state specific amount of air extraction from the premises in order to prove that you have taken out most of the carbon monoxide to go under the levels of toxicity. So today design are usually over-designed. There are papers regarding the subject, and there has been experiences made in the subject that prove that 7.6 air changes usually are over-designed. The 5 air changes of NFPA, according to our calculation, are also over-designed. And the idea of subtracting the air from the premises in a 20-80 method, which you actually subtract 20% of the air from the lower levels and 80% of the air from the higher level of the ceiling in order to catch also the carbon monoxide that lingers and also the smoke layer that holds up in the ceiling. So, and again, the other side. So our new perception, which is mostly a perception in way of proof, is using air circulation, rather air purification, to see what is going on inside. The goal is to just make the air move, not take it all away. So we use CO ppm concentration monitoring to check the levels of CO inside the premises, and according to that ppm threshold, the system either starts or stops. Airflow threshold, which is our way of saying how fast that you need to make the air move inside the premises here. You have a proof that you've already made some sort of an evacuation for toxic gases. We use an individual air circulation in parking levels for each individual levels, and sometimes in huge and bigger spaces we use separation according to the smoke zones, and we fragmentize the entire building, the entire level, to a few areas and make it specifically ventilated for that area that has high ppm. And maintaining and proving that we do by maintaining an airflow at a minimum of 0.5 meter per second air movement in a height of 1.5 meters, which is mostly the area that CO lingers when you have underground parking garages, and the emission from cars usually stands in the air. So, in order to portray our concept and the change in perception, we are using a case study of an underground parking garage that is actually designed by the Azriely-Group in Israel. It's the Azrieli High-Tech Center. And just one word about Azriely-Group. Azriely-Group is a very big real estate company in Israel, and they are in charge of a big number of malls and a big number of business centers, and one of their main centers is the Israeli Tower in the middle of Tel Aviv, which is a very nice building. Not the subject. Anyway, so when we look at the, how do you do a pointer here? Nice. When we look at the center here, we can see we have 4 stories, -4, -3, -2, -1. It comprises of a central atria, which is open throughout between the levels. This is the whole open area. And we have English courts opening on the outline of the building for, actually there was originally for bringing in light from the outside. Now, these are the courts, these are the opening. Okay. One thing also about the model is all levels have a 2.5 meter ceiling height, which is a low clearance height, which you can understand that you cannot prove smoke control with tenability of smoke height level on a 2.5 ceiling. It just begins with not going through the code. So when we started doing this, our methodology is starting usually almost in all of our models, we're starting from evacuation analysis, which we check how long will it take to evacuate the premises with the occupants inside the building, so we know how long we need to maintain tenability conditions. After that, we start with run N, which is usually run 0. We start with natural ventilation, which means fire only. Now, most of the time, you don't use natural ventilation to ventilate an underground parking garage. And these runs usually are here to show us what will happen if the system fails. And if the system fails, we have to know what will happen with the smoke. And actually, after that, we do... After that, we take both of them and we see the way that the system we design and how it affects the original flames, the original smoke. After the first run, 0 natural ventilation, we go to the original design of the electromechanical system by the AC engineer. We take that design and all the data from that and we run the simulation. If the simulation result is acceptable, then we're going to proceed to the next level and check the ventilation if the ventilation is sufficient enough. If it is not acceptable, we go back to the engineers and they redesign the system according sometimes to our advice. And sometimes they just do it on their own. After they redesign the system, we run it again. If it's acceptable, we go back to the last step and we check the ventilation test for the new system design. So in this case study, when we look at that methodology, we actually resulted in the following runs. The first run was really the natural ventilation, fire only. The second run we made was the fire scenario with the regional design electromechanical system. The third one was fire scenario with redesigned electromechanical system after the first original failed and was not acceptable. And the last, but not forgotten, the air quality simulation based on system design in run 3. I'm upside down. Okay. Now, evacuation analysis has been comprised of the following data. We used the basic model, and the assumption was the maximum capacity of cars in level -4, which is the level we made a simulation is 160 vehicles. During daily operation of a business center, we have around about 40% occupancy of cars in the premises, which is 40 vehicles in this specific one. 40% 160 is 40 vehicles. We took about the diversity of 2 person for 20 vehicles, 1 person in 10 vehicles, 3 person in 10 vehicles, got altogether 80 people occupying the premises. So we ran an evacuation analysis using Thunderhead Pathfinder software, and we use that as a part of the whole egress process. When we're looking at egress processes, it's not just the moments from use, not starting from the moment you start to move toward the door, but it comprises of the detection time that it takes for the system to start the alarm, and then it goes to the recognition and pre-movement time, which means mostly how long does it take to a person in the garage to understand that there is a fire? Well, sometimes it takes long, sometimes it takes less, but it's an open space. So if there's a fire in an open space, it probably will take less time. So we assume that time doesn't go over 60 seconds to see that there is an event and start egressing and walking toward the exits. We take that and we add up to all that the movement time that we got as a result from the Pathfinder simulation, and we multiply it by a safety factor of 1.5. That safety factor let us take under consideration things we didn't take under consideration in the simulation, like people getting stuck or needing assisting or falling on the way or just freezing on the way out because they're not sure where to go. Okay, now, by the way, okay, now just for a little nice round, we're going to show you the evacuation model. It's now evacuation simulation. Just a second. Where you can see, yes, very nice. So I don't know how good you can see it from afar, but there are small people walking here. You can see there is a group, I don't know if you can see really, but there is a group of people evacuating to the north exit and to the east exit, and a group of people to the west exit, and another group of people, which are really small because it's a really big garage, to the south exit. So that was the evacuation we did. And it took around about 70 seconds to evacuate 80 people from this underground garage. You run to the end. Yes, that's far after. And out. All right. The fire scenarios. The data we have used for the fire scenarios is following. The fire specification we use is a medium, is a car fire, 5 megawatt car fire with a medium growth. A maximum HRR is reached in 654 seconds. The burning area is 4.5. Soot yield is 0.01. CO yield is 0.02. And the graph, as you can see, does not decay. We do not decay the fire in our fire simulation in almost any simulation we run. It comes from conservative reasons, and we state that, well, worst case scenario that could be system of the sprinkler has failed and there is no decay, and the fire has caught up to the next car while the first car was already eaten up by the flames. So we use conservative reasoning and we do not decay the fire. And keep having this around. Well, the fire location was actually, we can see that it's level -4. Again, this is a top view of the first version of the architectural model. You will see there is a small variation There is a small variation between models of the runs because when we come and do CFD simulations, we actually do it during the time the architectures are still thinking about how the building will look. So a lot of time in the middle, they change the entire geometry. In this case, they change only the main atria shape. So this is version 1 of the model. The fire location is a car placed in level -4. And the air supply, the makeup air that we get from extracting the air comes mostly naturally from the main atria and from the English court we have seen on the outline of the building. The English court goes all the way from top till the lower level, so we can get fresh air flowing naturally. We have placed smoke detectors and heat detectors throughout the domain in the vicinity of the fire, around about 13/25-meter area around the fire. We have placed for readings, and we're using the smoke detectors actually just as an indicator time for smoke detection. They are not placed inside the building. There are no smoke detectors in that underground garage. We are using the heat detectors in the model as mean of indication of sprinkler time activation. We want to know what time the alarm will sound off, and if we want to model the decay of the fire, we'll go back to those sprinkler and decay that fire from the point of the fourth sprinkler opening up. So the smoke detectors are set to 3.28 volume, and the heat detectors are set to 68 degrees, and the response time index is fast response sitting on 50. So the second run we did, how long? Oh, well, they were late. We'll hold a few minutes. So we're going to hop over everything directly to the end. Okay. The first run we did was the run with the natural ventilation, and I'm going to go really, really fast on this video if the mouse will actually work here. Wait. Well, the first one was natural ventilation. I'm going to show you a side view so you can all see the way that this travels between the floors. You can see on the bottom is the level that has the burning car, and then level 3, level 2, and level 1, and smoke coming out through the main atria for natural ventilation and natural smoke control. All good, seeing that, traveling between floors. Next. Okay. The second design, the designer have decided to put most of the HVAC system, most of the HVAC fans through the English court. They actually use the English court opening to place shafts, and inside the shaft they place the fans, and we have all around the outlines a lot of fans. So they use that as an English court, and we can see from the side, same thing. You can see we had ducts going on from top to the first floor, the second floor, the third floor, the fourth floor, and each and every floor is being operated separately. That was the second design. That is the data that doesn't matter. And they used as well jet fans for congested corner and points where most of the jet fans are 90 degrees, moving 90 degrees of the movement of the air flow. This is not going to be easy with this mouse. Okay. The other way. Yes, okay. The result for the second run was not just not good, it was worse than the natural ventilation. Since we are extracting from out the outline, we actually made the entire smoke fill the whole premises rather than evacuate it. And again, we're going to hop fast to the middle. This is a 10 times real time, so, and with a little help. So you can see that for the time that it takes to egress the premises, the entire place is already filled with smoke. All right. So, right side, wrong side. The last simulation we did is the redesigned electromechanical system we used in run 3. The redesigned system is comprised of 4 shafts that are dividing the whole area into 4 smoke zones. First zone, second zone, third zone, and fourth zone, whilst here there is 1 shaft, second shaft, the third shaft, the fourth shaft. We are not extracting from all the shafts at the same time, and each shaft has 2 fans for each level, comprising a total of 8 fans per level. So we have 8 fans per level and 16 fans per level. It's 4 fans for each shaft and each zone. We have 16 fans per level, and we do not operate them at the same time. We actually can see it from the side. Each shaft had designated fans for each level, and we operate it by zone. When I say operated by zone, we'll get to that in a minute, the airflow that we were expecting to have in the simulation according to the new design is air coming in from the English courts and from the atria and extracted into the shafts. So we have air flowing, doing a push and pull action when the air will sweep with the smoke into the shafts. Okay, smoke screen has been used to divide and separate the level into 4 separate smoke zones. To redefine it, this is a smoke zone, this doesn't matter, all right. Okay. The third run was sufficient and acceptable by all the parties at hand for smoke management control. We were actually able to keep the smoke from traveling to the second level when we look at side view for that. I'm going to run through this. The main exhaust in the middle you see is smoke evacuating through the main atria area. Yeah? Very good. The second image we'll look at the top view so we can see the area the smoke covers when using smoke zone method. No. Okay, we're not going to see that because it didn't save. The changes from the morning. Okay. Looking at another video, we can see the slice for visibility. And the visibility slice is 2 meters from the floor, right? Yeah. It's a 2 meter from the floor of level -4 garage. And we can see that during the time of the evacuation and egress, we keep a nice level of visibility. Of course, disregarding the initial area of fire, which is the intimate area with the fire, you will never get clear visibility so close to the flames. But most of the egress routes, which are here and here and to here, toward this side and toward this side, are clear. And again, the same thing with the temperatures. Come on. You've got to use a mouse. We're looking at the slice of the temperature is the same level at 2 meters. You can see that the temperature are held in tenable conditions and do not exceed. These are not tenable. Did it the other way around. No, this is the visibility slice. Nice. Okay. Technicality problems are amazing. Okay. After running the third run, and we were satisfied with the result and it was acceptable, we have went over to run the ventilation run. The ventilation run, the entire system is working on half thrust, which means instead of 4 fans in each shaft per level, we're actually activating only 2 to get only half of the exhaust strength. And we use it according to the ppm sensors in the level, and then it operated by that. So we're actually operating this in this level in this simulation. We operated the ventilation system per the entire floor and not via the smoke zones. And the result we got is an air threshold that was at least 0.5 meters per second throughout the domain, except from a small congested area on the left side of the model that you will see, which was corrected and designed using a low-power jet fan. This is just an image because I knew I won't be having time for this video. This is an image of the airflow. We get the airflow intake from the English courts is a natural floor of makeup air, and we have the shaft exhausting the air, and by that making an entire circulation of air that does not purify the premises but ventilates the premises. Now, Israeli authorities in charge of this, the environmental authorities, has accepted this criteria as the criteria to prove the ventilation of underground parking garages. Also, the Israeli authority, the Fire and Rescue Authority, has accepted the idea of smoke zones as smoke control criteria instead of maintaining tenable condition on smoke layer heights. Furthermore than that, incorporating the push and pull method and working on means of action method, for firefighters to know where to address the flames in case of fire, and teaching the Israeli fire authorities that where there is fire, there will be smokes, and not using an interchangeable thought with the fire rescue team that smoke evacuation doesn't mean the place is cleared out of smoke. When there are flames, you will get smoke, and you will not be able to extract all of that smoke from the premises. So we decided to use the criteria for just keeping the egress route as plain as possible for people to evacuate and for the rescue team to come in and to understand that you can't have a vast space area like that without separating it to different areas. So I want to thank you for your time and your patience at this late hour after lunch and for my English. Questions, if we have time? No, we don't have